Hello everyone, welcome to my new video in my Mathematics Essentials series. In this video I am going to introduce inverse trigonometric ratios. Okay, so they are examples of inverse operations. Okay, what are inverse operations? You're already familiar with several examples at least. If you think of addition and subtraction, well, you know that if you, let's say you have x, and let's say you add some amount alpha, and then you subtract the same amount alpha, you just get back to x, okay? And similarly, if you did things the other way around, so if you were to subtract some amount alpha first, and then add back the same amount alpha, okay, you would just get back to x, and the end result in each case is no different than had you not done anything at all, okay? So addition and subtraction are examples of inverse operations. So notice it's also a two-way street. So if one's the inverse of the other, then vice versa. Okay, compare it to marriage. You know, if A is married to B, then you must have B also married to A. Okay, you know, you can't really have A is married to B, but B is not married to A. Okay, marriage is a two-way street. It's the same thing for inverse operations. Okay, so multiplication and division are inverse operations, as long as you're not dividing by zero, right? It turns out that our familiar trigonometric ratios, so we have the cosine of some angle theta, we have the sine of some angle theta, and the tangent of some angle theta. Okay, they have inverse operations as well. And the inverse operation for the cosine of theta is arccos. That's for cosine, and for sine we have arcsine. Oops, it's not of theta. Okay, it won't be of theta. It'll be of some some argument x. So we have the arcsine of x, and we have the tan of x. Oh, sorry, the arctan of x. Okay, so this is like saying, this is analogous to saying, addition has an inverse operation and we call it subtraction. Okay, cosine has an inverse operation and we call it arccos. Okay, so this here is the most common notation, but another pretty common notation for these is, I'll just do it for one of them. For instance, this is the inverse of cosine. They write a superscript with a -1. So this notation is pretty common as well, but the reason why this notation is more common is because this one can lead to confusion, because the superscript of -1 can easily be misinterpreted as a power. So as if you're raising the cosine of x to the power of -1. And by our exponent or indice laws, if we were to treat it as an exponent, if we treat the -1 as an exponent, this is what it would be. But it's not an exponent, so these are not equal. Okay, so whenever you see the superscript of -1, don't treat it as an exponent. That might lead you to wonder why such a notation would be adopted, because it is very common. Well, I imagine that it's due to the following. Okay, if we have some value of a function f of x, well, the notation for the inverse is actually a superscript with a -1. So I guess, this notation, although potentially confusing, isn't entirely without motivation or perhaps historical justification. I imagine that this would have been the motivation for its adoption. I don't know for sure. If you know, feel free to post in the comments and let me know. But yeah, to avoid confusion, I will just stick to the arccos, the arcsine, and the arctan. Okay. One more thing I would like to add is that these inverse operations are functions if you make the appropriate domain restrictions on cosine, sine, and tan, respectively, as functions. Okay. So if you make appropriate domain restrictions, the inverse functions will exist as functions. But if you're not too sure what I mean by that, don't worry. We're just not up to the functions section of the video series yet, so you can ignore that part about functions. Let's do an example. Okay. So let's say we have a problem. The sine of theta is equal to 1/2. Okay. Well, in previous problems that we've done, we knew what the angle theta was. Okay, so we were solving problems like, the sine of pi over 2 equals, and we had to figure out what that equals, and we would, consider a unit circle in this case, or in other cases a special triangle, and we'd end up saying this, sine of pi over 2 equals 1. But in this case, it's the angle theta which is unknown. Okay, that doesn't mean we can't think about special triangles and unit circles. It's just that we're going in the reverse direction to what we've been doing in the past. Okay, so given that sine of theta has an inverse operation, if we apply it to the sine of theta, so we take the arc sine of the sine of theta, we should be able to isolate theta, but we'd have to do the same on the right-hand side, right? So we'd have to take the arc sine of 1/2. Okay, and on the left-hand side, we would just get theta, and on the right-hand side, we still have the arc sine of 1/2. Okay, now how do we proceed? What do we draw? Well, if we were to look at the original equation, you can see it from this equation, but it's probably more obvious when we look at this equation. Okay, it's very easy to read mathematics without getting a sense for what the mathematics is actually saying. So I could just read this as sine of theta equals 1/2. Okay, but to really interpret this, what I should think to myself is that, okay, theta is some angle in a right angle triangle, right, such that the ratio between the opposite side length of theta and the hypotenuse side length of theta gives you 1/2. All right, so you should think of a triangle where this relationship holds, and maybe the opposite side length isn't 1, maybe it's 4, and the hypotenuse is 8. Okay, but as a ratio, this of course just simplifies to 1/2. Okay, so the side lengths might not actually be 1 and 2 respectively. Okay, the opposite side might not be 1, the hypotenuse might not be 2, but if they are not, then it's just a scaled up version of a right angle triangle where the opposite side length is 1 and the hypotenuse is 2. Okay, so we don't really need to worry about that. Okay, and if you think about our special triangles, you'll see that these trigonometric relations actually hold for one of those special triangles. So we could draw this one, okay, and we know that this is 90 degrees. Okay, this side length is 1, this side length is 2, this side length is square root of 3, okay. This angle is pi over 6, and this angle is pi over 3, okay. And now we just have to ask, okay, looking at this equation here, okay, this is like saying that theta is some angle with an opposite side length of 1 and an opposite side length of 2. Okay, remember, it might not actually be that, but the ratio will simplify to 1/2. Okay, so now we look at the special triangle and we ask, okay, well, which angle has an opposite side with a length of 1? And you can see, well, this side has a length 1, and it's opposite this angle, pi over 6. Okay, so we might be tempted to say that theta equals pi over 6 and be done with the question. But actually, we're not done, because there are more than one value for theta that we could substitute into this equation and get 1/2. And to see this, if you just consider a unit circle, okay, so I will summon a unit circle. Okay, well, you know that for any point on the circumference of a unit circle, okay, it's going to have an x component and a y component. Let's call it a and b. Okay, and a is equal to the cosine of theta. What's theta? It's this angle here. So the line between the origin and the point on the circumference, the angle it defines measured counterclockwise from the positive x-axis, that would be theta. Okay, so b, the y value, is equal to the sine of theta. Okay, and in our question, b was 1/2. B equals the sine of theta, and we found theta, or we found one value for theta. It was pi over 6. Okay, so we can treat the theta in our diagram as pi over 6. Okay, and this point on the circumference of the unit circle has a y value. We know what that is. So I'm just going to draw these dashes so that you see where this is going. Okay, this y value here I'll draw it in blue so it stands out, would be half. Okay, but you can see that this red point on the circumference of the unit circle also has a y value of a half. That's why I drew in the gray tick marks. Okay, so whatever angle that this red line makes, the one that we draw from the origin to that red point on the circumference of the unit circle, okay, that angle measured counterclockwise from the positive x-axis, okay, given that it has the same y value, that point here has the same y value as the green point, okay, sine of whatever the red angle is must equal a half as well, okay? That's the other angle we're looking for. I didn't mean to reference Star Wars. I'm not a huge Star Wars fan, but I just realized how that sounded, okay? So how do we find this red angle? Well, we know that this angle here, okay, between the red and the negative x-axis is also theta. And we know what theta is. We know that it's pi over 6. We know that this angle here, okay, that would be pi, right? That's like going all the way around like this. That would be pi, okay? So all we need to do is take pi minus theta. That would give us the red angle, okay? So pi minus theta, which we know is pi over 6, equals, when you get common denominators, this will be 5 pi over 6. Okay, that's the other angle we're looking for. So theta equals pi over 6 and 5 pi over 6. Okay, and you can see why this has two solutions, because there are two angles, okay, that will have the same y value. In other words, two angles for which the sine of those angles each give 1/2. Okay, now if we already knew going in that we needed two solutions, what we could have done is draw a cast diagram. Okay, so here's our cast diagram, CAST, and we can see from the initial equation that whatever the angle is, its sine is positive, okay, because we have positive 1/2 on the right hand side. So that means our two angles must be in the quadrants where sine is positive, and from the cast diagram we see that it's positive in this quadrant and it's positive in this quadrant. Okay, so we would know from the get-go that, you know, we wouldn't be getting angles in either of these two quadrants. Okay, now one last comment before I wrap up this video. You might look at this example that I've given here and think, well, it's a bit contrived. Okay, it just worked out nicely that the problem you gave exhibited, you know, those trigonometric relations in one of our two special triangles, and you're absolutely right. Okay, it was a contrived example, okay, because we've been working with the special angles. But if you had something that was nasty, for instance, the cosine of theta equals 0.53, okay, well this equation here doesn't really exhibit any of the trigonometric relationships in any of our special triangles. You know, we can't really draw in a unit circle nicely and reason about it. So, you know, in a mathematics exam, I imagine it would, you know, you'd be, if you were asked to solve this, you'd be allowed to use a scientific calculator. But if you would really want to solve this by hand, you know, in your spare time, one approach would be to use something called a Taylor series approximation. And to find the Taylor series approximation of a function, you need calculus, okay? And although I will cover some basic calculus in this video series, I won't be doing enough to get up to Taylor series approximations. That'll be for some other video series one day. Okay, so if you liked this video, well, it would make sense to give it a like. And you know, if you found it helpful, that makes me happy. If you want a notification when I upload a new video, just subscribe to my channel. Until next time, bye for now.